In this video, we'll be talking about pressure sensor. PX26 series 5 psi pressure sensor is the one that we will be using in the lab. This is how the sensor looks like. The two ports of the sensor, port 1 and port 2, and the 4-wire connections for power supply and the measurement. Before we look at the real equipment, I want to spend some time to look at the specification of the device with you together. The first item you can find from the datasheets is called excitation. Inside the differential pressure sensor we are using in this lab, there's a Wheatstone bridge. So the excitation is for powering up the Wheatstone bridge. Typically, we'll be using 10 volts DC power for the Wheatstone bridge and 16 volt will be the max. The next one is the output. This may be a little bit confusing, but let's try to understand it. We all know that the output of a Wheatstone bridge is proportional to the excitation voltage. So you have to specify how much the excitation voltage is when you are talking about the output. The device we are using is 5 psi, and on the datasheets, it reads out as 5 psi is equal to 50 millivolts, which means 50 millivolts is expected to be seen at the output when we are using 10 volt excitation voltage. There are some other very important information you can find about this device on the datasheets. We will not be able to go through them one by one. Those include the linearity, hysteresis, zero balance, stability. For example, if you want to do uncertainty analysis, those parameters will be very significant for you. Before using the device, we first need to calibrate it. This is a system set up for calibration. We're going to use a liquid manometer to help calibration. And this is our differential pressure transducer. Port 2 is connected to the manometer. And don't forget that our pressure transducer can only give the output in voltage, so we need another DMM to measure it. Let's put the schematic and the real equipment side by side. The liquid manometer, differential pressure transducer, which includes 4-wire connections. Out of the 4, 2 go to the DMM for measurement, and the other 2 go to the power supply for excitation voltage. A close-up of the system. 4-wire connections, transducer, DMM and power. The calibration process can be also understood as filling out this table. The first column is the pressure in inch, which is provided by adjusting the manometer. This will be converted later on to fill out the second column, pressure in psi. The last column is the output of the differential pressure transducer, which is the readout of the DMM. Here's our first set of data: 1.8 inch from manometer, 1.2 from DMM. Let's continue working on the table. This is 3.8 inch, corresponding to 2.4 millivolt. 5.4 inch, 7.4 inch, and 9.4. We've got the first and last column of this table. The middle one comes from the conversion between different units of the pressure. After having the complete table, what you want to do is to draw a calibration curve between the pressure and the voltage. For convenience, it's recommended to use x-axis as a pressure and y-axis as the voltage. This is a sample calibration curve for this differential pressure transducer. And the sensitivity of the device is exactly the slope of the calibration curve.